Welcome back, everyone. So to end day one, to complete day one, we're going to continue on the thread that was started a moment ago as we learned about unsupervised machine learning with a more in-depth discussion of dimensionality reduction, which we also spoke about is not just about reducing dimensionality, but can also be incredibly useful as a tool for building visualizations of high-dimensional data sets. And for that talk, we're going to hear from Dr. Bryan Scott, who is the DSFP postdoctoral fellow.
Thank you, Adam. I have to say that's still really weird to hear. Wow, okay. So yeah, talking about dimensionality reduction, I'm kind of curious, and I'm not going to give it away if you don't recognize where this image is from, but does anyone recognize maybe where, or can speculate as to where this image is from? I don't want you to actually do the speculation, but just raise your hand if you have any idea what it is from. Okay. No worries. Just one of the, probably the greatest work of sci-fi from the last 10 years, and I'll leave it at that.
Avatar?
Wait, what is it?
I'm not gonna, it's a spoiler.
Oh,
It's, yeah.
Avatar.
Yeah. A lot of dimensionality reduction going on in Avatar. Okay, yeah, they're actually. So the learning outcomes for this talk are to relate dimensionality reduction in the landscape of other learning techniques. So we've seen a little bit about what the formal structure of a learning problem looks like, and I'm going to try and place what unsupervised learning looks like and how dimensionality reduction has some aspects of an unsupervised problem and also some aspects of a supervised problem. By the end of the talk, you should be able to solve problems with dimensionality reduction, and in particular, you should be able to articulate why you would want to engage in dimensionality reduction on your data. And some specific examples that you'll have in the tutorial are to implement a principal component analysis on SDSS images, which is a very common use case for PCA, and to use T-stochastic neighbor embedding to produce a lower dimension representation of some recent Cosmos 2020 photometry. There's also a third bonus problem that is significantly more involved, where you could write self-organizing map, which is the other technique that I'll talk about. If you're interested in some further reading, I recommended this one earlier, but the Introduction to Statistical Learning is a great place. Lots of discussion of dimensionality reduction. I think in this one, there's also the Elements of Statistical Learning, which maybe is what I'm thinking of, has the longer discussion, but you'll find a lot of these concepts covered in a really foundational way in both texts. I also recommend the two papers that I'll talk about are Mapping the Galaxy Color Redshift Relation, Optimal Photometric Redshift Calibration. The title continues cut off, but this is by Dan Masters, who introduced self-organizing maps into cosmology. And I'll show some results from this paper, but it's a very readable paper and introduces self-organizing maps in a very cogent and easy to understand way. And then the original TSNE paper is actually shockingly readable. It's maybe one of the best written papers that I've encountered. You see it recommended every time people talk about TSNE, and it's because there really isn't a better way to explain what's going on than the way they actually explained it in the original paper. Okay, so some perspectives on dimensionality reduction. I realize this is more of a wall of text than I intended, but one way of thinking about a general unsupervised learning problem is that you are trying to infer a probability distribution over some feature set. You have some probability distribution X over n observations, X1 through Xn, and the subscript is indicating that this is a vector that lives in some d-dimensional space, and d could be anything, right? So we're very used to building intuition in 3 dimensions. The point of dimensionality reduction is we want to be able to use that intuition when our data lives in 30 dimensions or something like that. And we'll talk about how that manifests in the other perspective, but it's also very difficult to infer a probability distribution or to estimate a probability distribution in high dimensions. So dimensionality reduction can help you to infer that probability distribution. Yes, it's actually kind of a surprising thing But the supervised learning problem, where you're handed labels, is often an easier problem to formulate than this unsupervised and very unconstrained problem of tell me what the best probability estimate of the probability distribution that describes this data is. So in this interpretation of dimensionality reduction, our task is to find a lower dimensional or a compressed representation of the probability distribution that maintains important features of the structure of the data. And so basically what every technique is doing is it's favoring some features of that higher dimensional probability distribution that will be maintained in the lower dimensional representation or the compressed representation of the data. The other perspective on dimensionality reduction, we often actually cover this topic in the visualization section, is simply as a tool to visualize data. And this is actually how it's mostly used, I think, in astronomy, is really just to come up with visualizations to help us build intuition. So really, just gonna play. Okay, that doesn't quite look the way I wanted it to, but this gets the point across, which is if I have something that's moving, if I have something that's animated, moving in 4 dimensions, a 3-dimensional representation of that path with 4 dimensions is when you project it down and you trace out the path that that ball took, right? So that's a very simple example of a dimensionality reduction to create a visualization, is I want to show something happening in 4 dimensions, but I only have 3 dimensions. And of course, the really fun gimmick here is this is a 2D version of the 3D embedding of the thing that's happening in 4D, right? So there's a lot actually going on in making an animation like this. So I've sort of motivated this already, but what are some reasons why we might need or want to do this? Discuss this with your neighbor for a couple of minutes, and then we will share back. So let's maybe do that for 3 minutes, 3 or 4 minutes.
Yeah.
Yeah, okay. Yeah. That would be like
why do we want to reduce our lower dimension?
this is you know, like what do you do? Like this said, well,
Visualization to explain or interpret, to help explain and interpret data to an audience.
that's true. So is we're trying to find a or even if when we try to find you make it clear between each. Don't really think about my research right now is less than wow. Like just very so yeah, if it specific like color
So let's maybe finish up the thought.
yeah. All of the yeah, exactly.
Okay, so let's come back together. So does anyone want to share a abstract or a practical reason why you might want to reduce the dimensionality of the data? Yes, generalization of models in general is a big part of this, actually. Yeah, something that I don't even think I hinted at, but yeah, that's a really important one. We'll talk more about that. What are some other reasons?
Helps us better understand the data because we can look at numbers one by one and figure out that there might be structures in the data. We need visualizations and less dimensions can create better visualizations.
Yeah, I mean, this is getting more to the point, right? Like, I can visualize 2 dimensions really. Well, I can visualize 1 dimension, maybe the easiest. 2 dimensions is okay. 3 dimensions starts to get a little bit harder. 4 dimensions takes some work, right? 5 dimensions, I start to use my other senses, right? but people do that, right? There are cool examples of people encoding information in audio plus visual, right? So like you can envision in some sense up to maybe 5 or 6 or 7 dimensions using additional senses, but then anything harder than that, there's really no other option, right? You have to do some sort of projection down to a lower space. Were there other? Yeah.
My question is like when you are using the dimension relation, will it not affect like from that data? For example, like recently I actually announced this way, like supernova, when we are like checking the 5 dimension or the 3, you can understand how it is like explosion. Like when we are checking 2 dimension, stuff like
Yeah, so that goes both ways, right? Like you can add dimensions, which maybe helps your interpretation or opens up new physics, right? Like there are physics problems where the dimensionality is part of the physics. So if you don't have access to those dimensions, you just can't observe those phenomena. The process of doing the dimensionality reduction, right? We'll talk more about this, especially depends on what features of the higher dimensional probability distribution that you want to maintain for dimensional representation, right? So interpretation does become you have to be really careful about over-interpreting your reduced dimensional representation. Were there other? Yeah.
Some of your axes may not be totally independent. So you
yes.
Write them in the combinations.
Yeah, definitely, right? And this is a whole, not even just within the space of machine learning, but a huge part of linear algebra is finding orthogonal representations, right? Things that are truly independent and assessing that kind of independence. So these were the answers that I had. Computationally challenging. I don't know if that one was actually mentioned, right? But if you have a really large, 28 bands of photometry and 1 billion galaxies, that's a lot to throw. You have to throw a lot of compute at that to get answers out, right? This was what I was thinking of, was mentioned, was the mini algorithms have poor scaling behavior in higher dimensions, or they don't generalize well to high dimensions. So generalization really matters here. Interpretation for visualization was mentioned, and as you mentioned, some dimensions may, independent of independence, some dimensions may matter more than others. So we want to highlight that dependence, those directions that are more significant in some sense. So there's another interpretation, which maybe isn't a different interpretation, but you can think of dimensionality reduction as selecting features that you want to give your model, right? So dimensionality reduction is often the first step before you apply other machine learning techniques. You're selecting the things that you think are going to matter, then you throw other techniques at it to get results on labeled data, for instance. So worry about your data and worry about your features, and choosing the right features can matter a lot. So one question you might have is, why is this possible at all, right? If a process is intrinsically happening in higher dimensions, why would I expect to be able to eliminate information about those dimensions and still get something out? The big idea is this idea of sparsity, and we will do this. Cohort 6 has done this as an exercise in one of the tutorials from a past session. Cohort 7 will do this in the future, but there's this idea that the volumes grow in unintuitive ways as you go to higher and higher dimensions. And so data is sampling a smaller and smaller part of parameter space. So when you go to really high dimensions, there's always dimensions that matter more. So even problems that live in these higher dimensions you can eliminate some of those dimensions simply because the data isn't living in the full, say, 28-dimensional space. It's living in some certain directions in that 28-dimensional space. One of the issues is that there's no ground truth here. So I can't tell you that this algorithm does a better job of achieving a certain loss than some other algorithm. I have no ground truth. I have no way to say one method is better than another. And so this has led to a large proliferation in the kinds of dimensionality reduction schemes that you're going to encounter. I think it's important to think of this as a feature and not a bug, right? This is giving you a lot of options to solve problems. If one doesn't work well, try a different one. It probably will work well. Question the assumptions that go into each method, modify those assumptions. There's always some notion of how these probability distributions are related to each other, what features you want to emphasize over other. And the other thing is we should also always have different visualizations to compare, and this helps with interpretability. If doing one dimensionality reduction is obscuring some important information about the data, maybe a different dimensionality reduction will highlight that feature, and the combination of the two might give you intuition about the fact that both of these things separately matter. So just the visualization part is enough to really to view the wide variety of techniques as something that really helps you to solve problems. So we're going to cover 3 techniques. So principal component analysis, which has already been touched upon, but is really the cornerstone of dimensionality reduction. It's where people's intuition is built. It's also oftentimes the first thing that's presented when talking about machine learning at all. We'll talk about T-distributed stochastic neighbor embedding, which is a mouthful, and I really will just say T-SNE for most of the rest of the talk and most of the rest of life. And then we'll touch on self-organizing maps, which are something that often sounds really scary. I think even the name, like how does something self-organize, seems like really scary. They're actually a very simple idea. And once you get past some of the jargon and the usual presentation, it's fairly straightforward. So the first technique is principal component analysis, and I do apologize, there's a lot of linear algebra that I'm about to throw at you. I just wanted to include it for completeness here. So we define the principal components of a set of data as the sequence of best linear approximations of a smaller rank or a smaller dimension than the intrinsic dimension or the intrinsic rank of the matrix that these things are living in. So I think it's important to define these words because people throw around the word linear a lot, right? And we all have intuition for what that means, but we can make that formal. So by a linear approximation, what I mean is that there's some function, basically what I want to do is I want to find a representation of the data that looks like this thing. So I have lambdas, a linked Q vector of some parameters that I want to learn. VQ is a P across Q matrix with Q orthogonal unit vectors as columns, and U is some location that lives in this intrinsically RP space. That's a mouthful. I'll get back to this in a second, but what we're really doing is we're finding an orthogonal, we're finding basically just a orthogonal basis to describe our data. That's all that's going on. We can do that as an optimization problem. So we know now what a linear description of the data looks like. And whenever we have the word best, what we mean is optimization. So what I'm going to do is I'm going to minimize this sum. And one important thing to note here is that we often subtract off the mean of the data. So this is called recentering. I'm going to have you do this in the tutorial notebook. What's going on here is that HQ, which is this combination of these VQ matrices, is projecting the data onto a basis span by the columns of this matrix. So the data is being reprojected onto an orthogonal basis. So we can work out exactly what this reprojection looks like. And it turns out that this is defined by an operation called the singular value decomposition. Yeah, this SVD is a very common thing. It shows up in linear algebra all the time. There are lots of algorithms for computing it, so it's not something that you have to learn how to compute yourself. But the parts of the SVD have specific interpretations. In particular, the VI vectors that live in the V matrix as the columns of the V matrix are the principal components. So they are pointing in certain directions that define a best linear approximation of the data. And when you do the SVD, this D matrix that lives in the middle is a diagonal matrix, and all of the elements of the diagonals are the variance of the data that correspond to each of the principal components. So just by performing the SVD on your data matrix, you are decomposing into an orthogonal basis, and it's telling you, ordering the basis vectors by the variance maximizing directions in your data. So that's really useful. You now know which directions in your data matter the most, and you have a list of them. Go down and take, say, only those directions that matter the most, and throw away all of the other ones. And you have a built-in way of telling how much information you're throwing away by truncating, let's say, only 5 of 28 principal components or something like that. So this is cool. We started this process with the goal of finding a matrix that projects some high dimensional data into a small number of dimensions. And we were able to find this in terms of a well-defined operation that there are algorithms to compute, and that we can compute very easily in, for example, in NumPy. So this is the first interpretation of PCA as a dimensionality reduction technique. What we noticed, though, is that PCA is also picking out certain directions in the data that are variance maximizing. And so we've learned something really cool, and this is the interpretation that I think most astronomers have when they do PCA, is the variance maximizing interpretation. So that's what I'm going to have you work through in the tutorial notebook. Is you'll decompose SDSS images into the principal components and basically get do kind of a feature selection on galaxy images, and then you'll be able to reconstruct the galaxy images. Yeah.
What do you mean by interpretation? If you're telling me, like, are you saying interpretation is that people think that's the value of it? That's
Yeah.
Oh, okay.
The interpretation here is both of these things are mathematically true, right? There's no option to say the math is doing something else. How people think about it or intuit about it or think it's valuable is that it's picking out directions that are variance maximizing. PCA is not often used as a dimensionality reduction technique in the way that t-SNE is, or that self-organized maps are, but it does pick out certain directions that are better, or not better, that are particularly that are variance maximizing. They're telling you the most about the directions. So we'll move on to the second technique, which is t-distributed stochastic neighbor embedding. T-distributed stochastic neighbor embedding is an example of a stochastic neighbor embedding technique. I would not have guessed. So we're going to go through what stochastic neighbor embedding is, and then we will talk about why a t-distributed stochastic neighbor embedding is better than a different kind of SNE technique.
What does it stand for?
It's the student's t distribution. So it's like the Gaussian distribution. We'll come back to it. Okay, so PCA is really focusing on keeping dissimilar points in the high dimensional space far apart, but it doesn't do anything to ensure that similar points are well represented in the lower dimensional space, right? It's maximizing the variance, it's not minimizing the variance, right? So you're making a choice about, I care about things that are well separated more than I care about things that are closely separated. So this makes PCA a little bit hard to interpret, and you shouldn't ever over-interpret what the principal components are. The goal of stochastic neighbor embedding techniques is to give you a dimensionality reduction technique that has a little bit of additional structure or machinery sort of built in. So the way this works is we take a data set with some high dimensional components, which are indicated here by a script X, and convert it into a two-dimensional map, where the two-dimensional map script Y are called map points. So we're mapping points in high dimensional space into things that live in a 2D plane. The example that motivated the original t-SNE paper is probably the best performing example that anybody ever talks about. So t-SNE in particular is sometimes a temperamental technique, but this was doing handwriting recognition. So the goal here was to see where these images of digits that people draw, where they live in the 2D space. So can I tell that a 0 is different from an 8? And so what they find is that they're able to do that. That if I take all of these points, t-SNE will separate them into these clusters that live in this space, and then I can separately come in and I can label those clusters, right? So I can say, for example, that all of the 0s live over here, all of the 3s live over here, And interestingly, right, we can see that 3s and 8s live next to each other, right? So the vectors in the image space, which is some high dimensional space of the pixel values and images, the images that correspond to 3 and 8, those vectors live next to each other in that high dimensional space, and that mapping is maintained in the low dimensional space. So we gain some intuition for how these, the 3s and 8s kind of look similar to each other, right? So TSNE performs surprisingly well on this data set. Or sorry, yeah, this is TSNE, not just a random stochastic neighborhood. The key insight, yeah. Yeah. So the dimensionality of the original space here is going to be whatever the number of pixels in the original image is. So I forget this is a very famous problem, but you can actually download the raw data as well. I think these are like 32 by 32 postage stamps. It might be 60 by 60. What is 2? So the stochastic neighbor embedding techniques are taking things that live in some R equals 256 or whatever, and they're reducing it down to a 2-dimensional plane. 2 dimensions, the way people talk about this is they're basically some linear combination of the original dimensions. But you never interpret what there's no reason to interpret those dimensions. So all you're saying is you're saying that what's happening here is you're just showing that the different classes are well separated in length, and that they live close to each other. Yeah.
So
yeah. So there's a lot of ways to do it. I am not familiar with how every TC algorithm is doing it, but we're going to talk about what loss function is actually computing. And there are analytic, this is jargon for the rest of the week, but there's, you can calculate the gradient of the loss function analytically in terms of as you change coordinates, how is that loss function? It's not really a loss function because there's no labels here, but there is a function that is being computed. We'll talk about that in a second. Yeah. It's learning. That's what it's learning. So it's transforming the data into some linear combination. So the cool thing that should blow your mind here is that this technique somehow knows not only to separate 3s and 8s, but that it tells you that 3s and 8s live next to each other, right? So you can imagine this would be really useful if you said we're looking at galaxy morphology and you wanted to see that like barred spirals and boxy ellipticals live next to each other or something. That'd be really interesting. I don't know that they do. That was the problem I originally wanted to give you, and I couldn't get it to work. So maybe they don't, but it'd be cool if it did. Yeah.
Is there any way of uncovering what the like underlying functions are that are driving each of the axes, or is that kind of contrary to the point of like this visualization?
Let's wait until I say the things I'm about to say, and if that answers the question, let me know. If not, we can revisit it. Okay, so the key insight is that we're treating the distances in the lower and the high dimensional spaces probabilistically. So we're not looking for just like a mapping that minimizes like Euclidean distances between points. What we're looking for is we're looking for a mapping that preserves some or that minimizes some distance between the probability distributions around those points. So yes. So we're going to define 2 probability distributions. So P of J conditioned on I is how similar 2 points are, the distribution of similarity between points that live in the high dimensional space. And Q J conditioned on I is the probability distribution in the lower dimensional space. So we want those two probability distributions for how close 2 points are to be as close as possible. So that's the function that we're trying to do this. The way we do this is we calculate something called the Kullback-Leibler divergence. So this is a thing that's going to come up a lot. This is what basically, some caveats, this is what it means for two distributions to have a distance between each other. So when people need to compute distances in three-dimensional space, we use the Euclidean distance. When we need to compute distances between probability distributions, we use the KL divergence. And it's got this definition. We'll return to talking about the KL divergence probably in future sessions. One thing you should be aware of is that it's not a true distance because it's not symmetrical. So if I swap the points, I get different distances. Or if I swap the distributions, I get different distances. Yeah.
I didn't quite understand the probability of J given I. So if it's equal to 1, what does that mean?
I'll come back to that, right? But it's a distribution of similarities. So we're going to define the notion of 2 points being at a similar point in the space. And the way we're going to do that is by writing down this function. So we're saying there's some Gaussian distributions. They describe how similar data points are in the high dimensional space. So they take in some distances in the high dimensional space and some variance, sigma, that's a hyperparameter that we have to define. I don't know if anybody has used the word hyperparameter before, but a hyperparameter is just a bit of jargon. It's all of the knobs in an ML method that you get to turn to change its performance. So as an example, in k nearest neighbors, the number of neighbors that you're using to cluster things, that's a hyperparameter. So sigma is the hyperparameter for stochastic neighbor embedding. One other thing I'll say about this in just a second is, yes, in TSNE, there's a parameter called the perplexity. I'm not going to go into defining what the perplexity is, but it's what sets the variance. So we're not going to set the variance by hand ourselves. We're going to define something called the perplexity, which will set the variance based on the dimensionality of the problem. So it's automating a step for us. And as this came up, but I was going to skip it at a technical level, the training proceeds by explicitly calculating derivatives of the KL divergence as you vary the map. And there's different ways you can vary that mapping to calculate those derivatives. So TSNE is basically like any other stochastic neighbor embedding technique, but instead of using the Gaussian distribution here, it's using a T distribution to do this embedding. This was really confusing to me for a really long time. And so what I did is I plotted these two distributions. It doesn't 100% make sense to plot them in exactly this way, but this should give you some intuition for what the difference between a Gaussian and a T distribution is. So the blue curve is a T distribution, the red curve is a Gaussian distribution. And I would like you to take a second and discuss with your neighbor why you might prefer the T distribution over the Gaussian distribution.
This question is why we prefer to use T distributions.
It's written.
I feel like the values which says high or
No, I'm looking at the. Bryan, I have a question. Why do you lose so many more significant digits for the Gaussian? Oh. Maybe that's a point.
I'm supposed to see you.
Sure, bro. Why for one over the other?
Because I'm not certain. They just ask that number 54 to find out Gaussian distribution. come here to the T distribution. So I read Gaussian distribution for hardness. For
More precision.
Yeah.
So let's maybe take one more minute to finish up your thoughts.
That would be good thought. Where can we find this on this? None of them that we've seen.
The ones from this morning should be on the GitHub under data. So that's like 18 and save file. But these ones, I usually post these ones after because I don't want to give away answers to questions. But if you like them, I know some people really like having them. I can't.
Yeah, they're not on.
Okay, there's been some issues. Okay, so let's come back together. Let's come back together. So, does anyone have any thoughts as to why you might prefer to use a T distribution instead of a Gaussian for our probability distributions of the similarity between data points?
We were thinking that the T distribution not being so sharply, it might help with clustering. So if we go back to the right thing, like the 3s being so close to H, they may lie on the outliers.
That is a brilliant suggestion. That is almost exactly why. Were there other ideas? Yes. So in the, I'm gonna not say it as eloquently as you just said it, but there are points, say the 3 and the 8s, they are steering together, right? So the T distribution has different tails, and so it's going to separate points in a different way. So there are, so I plotted the ratio of these two distributions, and again, it doesn't 100% make sense to do exactly this, but the point is that in the tails, you have a lot more probability in the T distribution than you have in the Gaussian distribution. Yes.
When you're with Gaussian, every sigma you get farther away still matters the same amount, and all we care about is clusters staying together, and we shouldn't care that distant clusters move nearly as much as close clusters move.
Yeah, not so much thinking about clusters here, but yeah, I think that's also a totally valid way of thinking about the interpretation. The jargon here, let me see, is that this is called the crowding problem. So as I mentioned, there's this curse of dimensionality. So when you have points that are living in some really high dimensional space, they are far apart from each other. There's a lot of volume in 28 dimensions that isn't in 2 dimensions. So any mapping that attempts to take 28 dimensions down to 2 dimensions has to figure out some way of encoding that there's a lot more volume in 28 dimensions than there is in 2 dimensions. And so the way T distributed stochastic neighbor embedding is doing this is it's encoding that volume in the tails of the probability distribution, where there's a lot more volume in the T distribution than in the Gaussian distribution. So yeah, any questions about that? So the good news is in practice, it's import from sklearn or import TSNE from sklearn. We're going to talk about self-organizing maps. Self-organizing maps are one of these things that, again, it's like the name itself is a lot of jargon for some really simple ideas. It's basically k nearest neighbors combined with principal component analysis. And there's not actually a whole lot more going on than that. So a self-organizing map is a projection of data in some high-dimensional space to a 2D plane. So the same way that TSNE is projecting down to a 2D plane, but it's emphasizing that it's trying to preserve local relationships. So unlike a stochastic neighbor embedding technique, which has some explicit notion of similarity, a SOM is an example of prototype learning. So we just saw that. That's k nearest neighbors, where you have some prototype points that are supposed to represent the data, and those prototype points are going to have encode some way of relating 2 dimensions to 28 dimensions or 30 dimensions or million dimensions, whatever it is. So a lot of times these are given a lot of different names. So sometimes you'll see these prototype points called neurons. And so sometimes you'll see people say that a SOM is a neural network. technically true, but it's not what I think of as a neural network, like the thing we're going to study later in the week. Best matching unit is another bit of jargon that really just means these kind of prototype points. So I'm going to use prototype. I think that's the cleanest, least jargony way to describe this. So let's look at an example of a self-organizing map before we get into the details. So this, and I apologize, it's hard. I'll talk to Adam about how to improve the slides to make these images bigger. But this is a famous plot that you'll see in a lot of cosmology talks, a lot of photometric redshift talks. So what's happening here is we have some cosmos. I think this is like originally like 20 band, or I guess, let me see. In this case, this is 2, 4, 6, 8. So this is 8-dimensional photometry, and it's been mapped down into a 2-dimensional plane. And I believe this is colored by the density of points, or it might be colored by the redshift. So you see these plots where you color them by different things and do different interpretations. One of the things is these boundaries. So I think this is actually colored by redshift. These boundaries are telling you about degeneracies, right? So if you are looking at 2 points that are right next to each other on a boundary, so they have different redshifts or different labels, those points are lying right on the degeneracy that is making it difficult to classify those 2 points. Okay? So what the SOM is doing is it's preserving those local relationships. So you can sort of trust those local relationships, 2 points that are right next to each other that are different. That's an important difference. Unfortunately, what you sacrifice by getting the local kind of things right is that the things that are happening at larger distances in the map are not telling you anything meaningful. So a lot of people try and over-interpret self-organizing maps. You have to be really careful about what is actually being preserved when you do the mapping. So every point in here corresponds to some photometry, right? Some 8-dimensional space. So every point is a 2D representation of some 8-dimensional data. And so you can go in and you can say, this point right here corresponds to this photometry. So we can make this rigorous. So a self-organizing map is a 2D grid of k prototype points that live in some space of dimension p, and these are parameterized by some integers, right? So what we mean by that is we mean that the self-organizing map is, say this is like 64 by 64. The self-organizing map has points that are like 0.40, 0.60 in x, 0.40 in y. So those are our parameters. And what we're going to do is we're going to map all of the data that lives in 28 dimensions down to those 2D ordered pairs. So the way we're going to do that is we're going to compute all the Euclidean distances of all the points in the high dimensional space. And we're going to find some prototype point, and we're going to find the closest one. And then we're going to update all of the prototype points around that according to this function, which is just taking the distances between the data and the prototype points. So what we're doing is we're moving the prototype points closer to the data. So we're deforming this 2D, or we're deforming this surface so that it best represents the data. That's all that's going on. So that's what I said here. So the big idea of the SOM procedure is this bends the 2D plane so the prototype points approximate the data in some sense as well as possible. And as I said, the intuition here is that this is just k nearest neighbors plus PCA. Just a little bit of jargon, this is also an example of competitive learning because all of the prototype points are competing to be the best prototype point. And then you move on to the next prototype point and the next one and the next one, constantly deforming. Yeah, so what this is doing is it's maintaining the topology, the kind of behavior on the surface of the high dimensional space in the low dimensional map. So I give you some pseudocode for implementing a SOM as a challenge lecture in the tutorial. Happy to talk more about SOMs. As I mentioned, they're very common in the PhotoZ community right now and in other parts of especially cosmology and galaxy evolution and things like that. So you might encounter them, and there's a lot of caveats about their interpretation. Speaking of caveats, just to close out, so when you're doing principal component analysis, be really careful about interpreting them. They're usually not physically meaningful, but they still can help you to make your data more manageable. It doesn't have any way of telling you what the variance is about, right? All it knows is it knows how those points are distributed in the space, it doesn't have any notion of uncertainty. So the variance maximizing direction could be a direction that is really the most affected by some noise, or it could be that that's a physically important direction in the data. And the extreme example of this is it doesn't know what to do with missing data, right? So a lot of data sets that you encounter in person are simply missing values. And that's a really extreme example of not knowing where the variance in the data comes from. There are extensions of this. You can look up this phrase, expectation maximization PCA, which is a bunch of jargon, but that's another kind of standard technique that you can think about for handling missing data. TSNE is also really subject to the presence of noisy dimensions. So there's some really powerful examples where TSNE will find structure in data that doesn't have any structure. It's just random noise. It's hard to interpret structure in TSNE plots. So I showed the digits example where everything was like really nicely separated. As I mentioned, that's the best example of any stochastic embedding technique that I've seen. I'm sure there are other cases where it works really well. You do see people do use this technique to visualize things in papers. It does work, but very often you're not going to well separate your, like you'll get clusters, and then when you color points in those clusters by the labels that go with them, they'll be separated but not separated super well. It's very hard to interpret. If, however, things do get really separated in the TSNE plane, that does mean that your classification later, your supervised learning problem, or whatever you're doing this dimensionality reduction to enable, is likely to work really well. The problem is, if it doesn't work, if TSNE doesn't work really well, that doesn't mean that you're not going to be able to do a classification or separate out your classes or whatever. As I mentioned, there's a lot of choices for how to build a self-organizing map. Every self-organizing map is different because of those. This is true of all dimensionality reduction techniques and all unsupervised learning problems. There's no ground truth or correct SOM, but the fact that SOMs vary a lot tends to matter a lot because people want to overinterpret them because of these very beautiful plots that seem very meaningful. Another thing to be really aware of is that cells in a self-organizing map might correspond to like one data point. And so you really want to care about how many data points for coloring that specific cell in the SOM, because if you only have one training point that's covering some huge region in some high dimensional parameter space, you really have not constrained that very well. And then, as I mentioned, SOMs really aim at preserving local structure at the cost of preserving global structure. So if you care about large scale things that are happening at large scales in your data, SOMs are not going to tell you a lot about that. Okay, so that's all that I had in terms of.
And one more quick caveat.
Yes.
TSNE is not 100% reproducible either. You can run on the same data set, the same algorithm. Things are initialized slightly differently. You may get different results. That's another thing to keep in mind when you're planning to use TSNE.
I was going to say, yeah, initialization is also a big question. So a lot of times these algorithms will be initialized like in the principal component plane. But that's a principled choice, but may not be the most efficient or computationally like best choice. So there's often a lot of choices about what is your initial choice of that 2D plane, especially like in self-organizing maps is where I've seen this come up, is when you're picking how do you assign those prototype points to start out with, that matters a lot for how quickly things are going to converge. You also have a lot of choice about when you define convergence or some notion of convergence. All right. So yeah, I think that's all I've got. So there's a tutorial notebook in the Git. We're going to have you first implement your own PCA. What I would like you, I don't know if I communicated this as clearly in the text of the tutorial, but what I want you to try and do is implement your own PCA and see how it differs from the version that is in sklearn. So you're going to get experience using both. PCA is one of these techniques that's straightforward enough because the SVD is a standard operation that it's very easy to. I never want to use the word easy when teaching. It is all very hard, but it should be straightforward to implement PCA. But your results may be a little bit different from what's in the sklearn version, and I'd like you to comment on what that difference is, and we'll talk about why that is different in the solutions. And then the second part is I've given you 28-band Cosmos photometry, and I'd like you to build a TSNE visualization of that 28-band Cosmos photometry. And I've also given you some categorical variables, which are the redshifts of that data. So you should color the points in your T-SNE plane by redshift and see if you can use 28-band photometry to separate out redshifts in the two. And I left this in. We can talk about interpreting. I ended up taking that out of the tutorial notebook. But if you're interested in how to interpret SOMs, we can talk about that.
Something that you mentioned about states that like you're looking for like linear spaces and solvable multiplices. But what if you have like ratios, features, products, or anything non-linear? Is there any way my relationships along exact states?
Not 100% sure that I follow your question. But I'm reminded of Adam mentioning earlier that one of the reasons why PCA is hard is that it has a scale dependence because it's maximizing variance. So if you're like, yeah, I'm not sure if that answers. That's my first thought. Yeah. There's also, maybe this is more along the lines of our principal curve analysis, where you try to find principal curves in the data. You can do principal surface analysis. These sorts of things may be more applicable to that kind of problem. But again, I'm not 100% sure if I have questions. Okay, that's all I got. So yeah.
Notebook's in the repo, so we're going to start working on the notebook now. The offer, the AC is working much better. It's pretty obvious to everyone, but the room next door is still a little bit cooler. So if you want to hop over there, that is fine.